so excited to talk to you guys about nuclear magnetic resonance, or as Sophia likes to call it,
NMR.
So come on! Hey guys! This is the nuclear magnetic resonance instrument. And now Sophia's going to explain how it works.
So, I have an organic sample here, and I'm going to load it up into our holder. And the way this works is I'm going to place it on the tire rack of science, and I would calibrate the computer so it would grab the sample and it would load it in, and there's a huge magnet in here, and that's why it's called nuclear magnetic resonance.
Hey guys, so we're just going to jump right into our topic and talk about why NMR is so special. And it's so special because it really takes this point that a nucleus can behave like a magnet. And what the NMR does is it applies a magnetic field to the nucleus, and it measures the amount of energy needed to bring that molecule into resonance. And we'll talk about what this resonance topic means a little bit later. And in saying that, we can conclude that nuclei in different electronic environments require different amounts of energy needed to bring those molecules into resonance. And finally, when the NMR is done, it provides us with various signals and peaks which represent the actual energy needed to bring the nucleus into resonance. And these signals and peaks can be integrated in order to determine different structures for various organic molecules. And finally, hydrogen atoms can behave as magnets in proton NMR, as well as carbon 13, nitrogen 15, fluorine 19, and phosphorus 31.
Hey guys, now we're going to talk about the chemical shift and what that actually means. So, if we're going towards the zero, it's considered upfield. If we're going the other way, it's considered downfield. Kind of interesting in the way that's named. So, if we're going upfield, it means that the atom of interest is more shielded. What that means is that it's close to an electronegative molecule. So it's going to feel that shielding from those electrons. If we go the other way, if we go downfield, it's considered de-shielded. Okay, so now we're going to talk about what's going on inside of this magnet. So, let's say for simplicity's sake that this is a nuclei, and the entire structure here is the NMR machine. So, when we turn the magnet on inside of the NMR, we have an induced magnetic field. So, the nuclei, when it's in parallel with the magnetic field, it is in its low energy state. However, when we shine some light onto it, the nuclei, we get its higher energy state. So it switches, and it's opposing the magnetic field from the NMR.
Hey guys, so now that we're done talking about NMR and how to use it, let's get some insight on how some experts use it in their research. Hey everyone, I'm here with Jeremy McCallum, PhD, chair of the chemistry department here at Loyola Marymount University. And I just want to know how you use NMR in your research and why is it so important?
Great question. So NMR is a crucial part of our research because we're constantly synthesizing new molecules. We normally use proton NMR and carbon 13 NMR. Proton NMR is more sensitive, and the advantage of that is it allows us to determine the actual structure of our compound.
We're watching that in the 45-minute video from your class.
Good call, 45-minute.
Hi everyone, I'm here with Dr. Lambert Duzema, PhD, and he's going to explain to us the benefits of NMR, and he's going to try to dumb it down a little bit too. So I'll let you take the floor.
All right. You have specific questions? Or?
Well, what is the benefit of NMR?
So the big benefit with NMR is that you can figure out structural information about a compound. So if you go in the lab, you synthesize some compound, you're not sure exactly what you made, NMR can help you figure that out.
Hello everyone, we're here with Emily Jarvis, PhD, one of the professors here at Loyola Marymount University. And we just want to ask you how NMR comes up in your research, particularly in your field of chemistry.
Well, NMR can come up in a lot of different ways, but one way that it's been coming up just even today with my research student is in looking Emmett.
See you there, Emmett.
All right. Is looking at, we're trying to determine a transition state structure for a chemical reaction where water is attacking an organic species. And there, it doesn't seem like typically we would have water being oxidized, but this is exactly the chemical reaction we're looking for. And one of the ways that it seems this might occur is through stabilizing this transition state with hydrogen bonding effects. Now we're able to look and more specifically go through and check different hydrogen bonding structures and see which would be most stable, but also how distinctly those would show up in the NMR so that we can possibly, if we get these NMR spectra experimentally, we can exclude some of the possibilities.
There you have it. Wow. Hey everyone, I'm here with Dr. Shiraki. She is not only one of my mentors and best friends, she is an amazing professor, and she's going to tell us what she likes about NMR.
Okay, so NMR is one of my favorite techniques because it tells you so much information about the structures of organic compounds. And there's a lot of different variety of NMR techniques. You can do variable temperature, and you can get information about kinetics. You can add, you can see the difference between stereoisomer